It's a bit difficult to see you, but I think it's probably better to take questions during the talk rather than at the end. There will be some time at the end, but if you think of something, do sort of wave and interrupt me, and I'll deal with it at the time rather than we get to the end and I realise I failed to explain something important with the first slide. I'm sort of starting from a position that you know something about Ceph, this being a Ceph conference, and I'm going to try and tell you a bit about what is interesting about the way we at the Sanger have used Ceph, where we perhaps differ from other people. The idea being that if you were, say, coming to the Sanger to work on our Ceph cluster, the sort of things you might want to know. So I'll start by giving a bit of background about the Institute and our use of Ceph and how that's grown. Then I'll talk about how we deploy Ceph with Ceph-ansible. I'll talk about how we monitor and manage it. I'll then finally talk about some benchmarking and upgrades, and I'll finish with some problems we've had and things we like about Ceph. So the sort of the bad bits and the good bits. So this is the Sanger Institute. This is a slightly dated now aerial photograph of the campus. The Institute was founded in 1992, and it really specializes in gene sequencing and genomic analysis. We were the single largest contributor to the sequencing of the human genome, and we continue to do a lot of both gene sequencing and analysis of gene sequencing. Typically, that's been done on batch-based clusters, so LSF, if you're familiar with LSF, and we have about 20,000 cores available in that batch-based clusters. And to support that kind of work, we have quite a lot of storage. If you talk to people about at CERN, they will describe themselves as high-performance computing. We're a bit more high-throughput computing, rather than having in very, very parallel compute jobs that will talk to each other using MPI or something like that. Typically, where our scientists are reading in large quantities of data and then performing some relatively memory-intensive computation on those data and then writing large data out again. So to support our work, we have quite a bit of Lustre. We have about 15 petabytes of Lustre storage. Lustre is a fast network POSIX file system, and about 20 petabytes of iRods. iRods is an object store, in some ways like Ceph, but its particular strength is it enables you to store significant quantities of metadata along with your objects. So typically a sequence file will be stored along with which machine it was sequenced on, when the samples came in, dates and times, and that sort of thing. And over the last few years, we've been looking at adding OpenStack to our computing facilities. We now have about 10,000 cores across our OpenStack suites. We've got an OpenStack instance running the OpenStack Pike release and one running the Queen's release, and we're in the process of migrating our users from one to the other, and then we're already starting to look at Rocky and subsequent releases. And we started off with Ceph as a way of providing storage to OpenStack. I think that's quite a common story here. And rather than having one Ceph cluster per OpenStack, we have one Ceph cluster, and all of our OpenStacks are just, from Ceph's point of view, different clients to that OpenStack. Finally, we also, when we started with Ceph, thought we'd use the Rados Gateway feature. We thought our scientists might want to use S3 to collaborate and share data. As it turns out, that's been wildly popular. Last time I checked, about 90% of our Ceph cluster was devoted to providing storage for S3 through the Rados Gateway. And that's not just people sharing, our scientists sharing objects with one another, but they've actually built entire web front ends on the top of that S3 service. So we have a thing called GenServe, and if you want to get sequence analysis done, it gives you a web front end. You can upload sequences and manifolds and all that sort of thing, and it does it for you. And really, that's quite a thin layer on top of S3. So my team is informatics support. We manage all of the things I've just talked about, all of the scientific compute clusters, the storage, all that sort of thing. We have other people in the Institute who do infrastructure, so networking. We have 4 data center halls on site, so we have a specialist team that handles those and the hardware work, and we have service desk who provide that sort of first-line support to users. I mentioned this because throughout this talk, I will be talking about how we've managed to offload bits of running Ceph onto some of these other teams. Basically, we're busy or lazy, take your pick, and it's been, for things like hardware work, we hand that off to the data center team because it frees us up to do other things. So that's who we are. We started off with, and all of our Ceph clusters are on identical hardware. If you're in one of the keynotes earlier from Supermicro, they talked about their 4U storage servers. we started with 9 of those. We now have 51 in our production cluster. And you can see, if you like hardware, here are the specs, 0.5 terabyte of RAM. We have Mellanox 2 times 100 gigabit networking, and we bond those together. So that gives you one faster interface, and when we run the Ceph private and public cluster networks using VLANs on top of that bond. We have a couple of small SSDs for the operating system, and then the main storage for our OSDs is 66 terabyte SAS drives. And then we have two terabyte NVMe cards for in FileStore, the journal, and for BlueStore, block.db. So each of those NVMe cards is providing the journal for 30 OSDs. We found as we grew the cluster that particularly during a significant rebalance, the monitor store could grow quite large. I think the largest we ever saw was 200 gigabytes, and that was getting embarrassingly close to actually filling the file systems. So we later bought some dedicated storage for our monitor stores. We started in 2016, and so we started with Ubuntu Xenial. We are now running Bionic everywhere except our production cluster. There was a problem with the Rados Gateway package for Bionic in Luminous, in that it's linked to the wrong version of libSSL, so you can't actually use TLS on Bionic, or you couldn't until recently. We've been working with Canonical, who support our Ceph clusters, and there are now Bionic packages for the Rados Gateway for Luminous, where you can use TLS. As I say, we started with Joule, and we're now running Luminous everywhere. I'll talk a little bit about that upgrade process later, but essentially from our point of view, it's pretty painless. Give you an idea of the timeline. I started at the Sanger in 2016, the summer of 2016, when we had basically no experience of Ceph. We'd sort of set up a toy OpenStack using some spare hardware we found down the back of a rack. And then later in 2016, we bought some dedicated hardware. We started out with 9 of those Supermicro boxes in 3 racks, 3 in the bottom of each rack, and the rest of those racks were filled with the OpenStack compute nodes and such like. So we started off with about 3 petabytes of raw capacity. Then in 2017, we essentially took an extra rack, filled it up with Ceph nodes, and put those adjacent to all of our existing racks. So they were still the same failure domain because we were using the same switches and cross-cabling the networks through. So, and then at the back end of 2017, we bought another rack, and this was our proposal for future expansion. You get 9 4U boxes in a rack, along with the switches and such like, and then you just sort of plug it in, turn it on, and away you go. So as of now, we have about 18 petabytes of raw capacity. We've used about 40% of it now, so I don't see us buying any more hardware this year, and that's in 4 failure domains, 3 of which are 14 servers and 1 that's 9 servers. Last year, we bought a test cluster. When we started off with Ceph, we talked to our users and they said, look, we only really want it for scientific workloads, so if it goes offline at the weekend or what have you, we're not that fussed. Great, that meant we could be quite flexible, we could be quite agile about how we made changes to our production cluster. But inevitably, as time goes by, Ceph proved itself to be very reliable, so people started building websites and such like on the top of our production, OpenStack and Ceph, and that's meant they've been more risk averse and we had to become more conservative. So we bought a small test cluster that's just 3 hosts, a petabyte of raw capacity, and that let us do things like try out the Luminous upgrade, try out the migration to BlueStore, that sort of thing in an environment that doesn't disrupt our users. Our last bit of Ceph is we have a disaster recovery site in Slough near London, and we have, again, 3 hosts, 1 petabyte raw capacity there, so not much. A quick show of hands, who is at least passingly familiar with Ansible? Pretty much everyone, good. So I won't say much about that. For those of you that haven't encountered Ansible, it's a configuration management system. It's agentless. There's not something continually running on the target server. Rather, you have an Ansible server that basically SSHs into your target machines and updates their configuration to match what you specify, and it uses YAML files. And Ansible has the concept of roles. So, for example, a web server will be a particular role, or if you want to set up your servers to talk to a smart host, that will be another role. And within the Ceph project, there's a thing called Ceph-ansible, and that's basically a series of Ceph-specific roles for the sorts of things you want in your Ceph cluster. So OSDs, Mons, Rados gateways, all that sort of stuff. And then playbooks, both for straightforward configuration and for rolling upgrades. We picked Ceph-ansible at Sanger because we were already using Ansible for our configuration management. And so we were going to use Ansible to manage our Ceph cluster, and then we discovered that someone else had already done most of the hard work for us, which was great. When we started with Ceph-ansible in 2016, it was quite a young project, so our initial deployment was basically just, we took a branch of what had been a commit on the master branch upstream at some point in the past. Ceph-ansible has become rather more mature in the meantime. We used versions 2.1 and 3.0 for dual, and we're now basing our deployment branch of 3.2 for our Luminous clusters. We have a number of Sanger-specific modifications to upstream Ceph-ansible, partly to set up our local things. So that bonding I alluded to earlier, we set that up with a Sanger prerequisites role, along with configuring our local DNS and email and all that kind of thing. Then we have a role for S3 user management, because we don't want to have to do that. The help desk have a thing called Rundeck, which gives them a web UI to administrative tools, and we've written a playbook that essentially is a receiving end for that. So the Rundeck SSHs in as an unprivileged account and talks to our server, which then works out what to feed to Rados Gateway admin for user management, quota adjustments, that sort of thing. We use Let's Encrypt, which is a free CA for TLS certificates. So we use it for HTTPS for our Rados Gateway server. Now, Let's Encrypt is free, but the certificates are short-lived. They last about 3 months, so you have to automate everything to do with that. So we wrote a playbook we wrote a role to do that using Ceph-ansible. It automates generating the challenge responses, getting a new key and certificate, and then deploying that across our suite of servers. If you're interested in that, think you might want to use that yourself, there's a GitHub repository with the URL at the end of this talk, so we'll come back to that. So you need to tell Ansible about your servers, and you do that with a thing called an inventory, which can either be a static file or you can have a script. We chose to use a dynamic inventory. We have one script per cluster, which means running Ansible on a different cluster is simply a matter of specifying different inventory script. And we have a bunch of utility functions that all of our inventory scripts use, which means we can reuse our code. And this is just sort of the broadest of outlines of the sort of things you can do in a dynamic inventory. So you can see here at the top, we specify our hosts. Then we can say which hosts have which roles. So here, obviously, we're specifying the monitor nodes. You can then configure particular variables you want for the services you need. So here, for the Rados gateways, we're specifying the interface to use, and that's one VLAN on the bonded interface I talked about earlier. Also, Ceph-ansible lets you set up pools and such like. So here, we're specifying placement group number and the name. This is the pool used for the data for the Rados gateway. And similarly, you can specify keys. The names here are OpenStack pools, OpenStack keys, but as it happens, they don't need to be OpenStack specific. You just specify them, and then Ceph-ansible does it all for you, which is quite nice. So that's how we deploy our nodes. We have some Sanger-specific roles for our local modifications. We have a few bug fixes. If you look at Ceph-ansible upstream, there's odd sort of picky things we've got pushed upstream, and then we have a few more fixes that we just keep locally. And we also template collectd, because we use collectd for collecting metrics from Ceph, and there's a Ceph plugin, but it needs to be told individually about every daemon on every host, which is tiresome to maintain, so we do that with Ceph-ansible. As we configure each node, we also configure collectd. Which brings me nicely onto metrics and monitoring. Hopefully you can see that roughly well. This is our dashboard. It's a Grafana dashboard. We've had it the same for a number of years now. When I first produced this slide, we used about 5% of our cluster. Now we've used 40%. And this is what we use as an at-a-glance idea of the state of our cluster. So we've got at the top here the number of OSDs that are up and in, 3,060, that's all of them. The monitor quorum, how much space we've used. And all of these are color-coded. So if you lose 1 or 2 OSDs, it'll go orange because that's not something you need to worry about. If you've lost more than the host's worth, these will start to go red because that's a sign that you need to stop what you're doing and go and look at it. We then have the throughput of the cluster. On the left-hand side here, the client throughput. On the right-hand side, going through the Rados gateway. And then a bunch of load metrics, so CPU, the load, network traffic, swap. And then at the bottom, we have a bunch of solid-state drives, which have a tendency to fail without much warning. So we keep a long-term track of the wear metrics for both the SSDs we're using for the root file system for our servers and the NVMe cards we're using as cache. And then finally, this is a record of the most worn solid-state device. To give you an idea of the volume of metrics, with Joule, you get about 19,000 metrics per server. In Luminous, that's gone up quite a lot. A server that's just running OSDs in Luminous is producing about 25,000 metrics, and for one that's running the Rados gateway as well, that's more like 28,000 metrics. And we found that as we migrated our production cluster from Joule to Luminous, that's quite a significant extra volume of metrics, and our metrics service started to struggle a bit. So that's perhaps something to be aware of as you migrate to Luminous, that the sheer volume of metrics you can collect from a Ceph cluster gets pretty big. If you're in the previous talk about looking after your Ceph cluster, you realize that metrics are only one part of looking at the health of a cluster. You also need to monitor it. Our infrastructure colleagues run a Nagios setup, so we use that. And as well as looking at server uptime and that sort of thing, we also have some Ceph-specific monitoring. So Nagios is putting objects into a pool and then getting it again, and also putting things into S3 and retrieving them from S3. So that gives us not only are all the servers up, but the cluster is functioning in good order. And that's quite useful as sort of early, often if the cluster is becoming stressed and response times are starting to degrade, Nagios will give us a warning before our users start complaining, which is nice, because it's always good if your users come to you and say, is there a problem with Ceph, to say yes, and we're working on it, rather than to sort of look rabbit in the headlights, oh dear, is something wrong? The last bit of monitoring is we have a script that runs nightly to check whether there are any OSDs down, and then that emails our hardware team, who can then manage replacing the disks. That's something we do nightly because a failed disk just happens. It's not something that needs addressing urgently. When we started with Ceph, our DC team colleagues were a bit wary of it. Ceph does have this reputation for being complicated, and they were quite unsure as to how to deal with failing disks. And the initial thing, I sent them a long checklist, and they were like, no, this is too complicated. We need something more straightforward. So we have a script that they can now run. And this is the sort of output you get. So you run it on an OSD, and it tells you which disk it's on. It looks at the smart status of the drive. You can see here the drive is about to fail. If the smart health check is okay, which we often find it will be with the drive, even when the drive is well on its way out, and we've seen lots of medium errors, it will then go through the kernel log and see if there are any error messages there. And then it tells you what you need to know if you're going to replace that drive. So the serial number is always good, because it's not always entirely reliable which drive bay will appear as which LUN, unfortunately, with these super micro boxes, which can be a bit of a bore. So we always provide the serial number to give our data center colleagues the obvious thing to check. Pull the drive out, is it the right serial number? Yes, great. If not, plug it back in, Ceph will sort it out. Finally, we blink the light on the drive bay and tell you which journal partition the journal was on, because if you're going to rebuild that OSD with a fresh drive, you need to use the same partition. And then we put up this little ASCII art map. If you ever open one of those 4U Supermicro servers, this is how the 60 bays are laid out, and basically X marks the spot, tells you which drive to pull. Now, I understand from the keynote this morning that eventually in Nautilus or maybe Octopus, Ceph will do all of this for you. In the meantime, we've written a bunch of scripts that do it, and this makes our DC colleagues' life much easier. They know which drive to pull, there'll be a light on it, and they can check the serial number. Now, a failure mode you may have seen with drives that are failing is they appear to vanish from the host. The device node entry disappears, the kernel says, I can't find the drive anymore, and obviously then you can't turn its light on because there isn't a device node to associate it with it, and our script in that case lights up everything else. So you then say to the operator, well, pull out the drive that doesn't have a light on, that's probably the one you want. All of this stuff is quite specific to these Supermicro boxes, though the bit that knows about the drive layout is a function you could pull out and replace. So this sort of code is also available on GitHub, and there'll be a URL at the end if you want to download it. I don't really believe benchmarks, but everyone seems to like them. If you go to all the vendors out there, they will have benchmarks. I think you should generally take them with at least a pinch of salt. That said, we did some benchmarking over Christmas when our cluster was quiet. This was when we were still running Joule and File Store. And this is just using the Rados bench utility that comes with Ceph, running it on some of the cluster nodes themselves, so taking advantage of the available networking within the cluster. And you can see with the rand read benchmark, we got just over 100 gigabytes a second, which is, that's pretty good going. Similarly, sequential read, about 90 gigabytes a second, and with write, about 10 gigabytes a second. We did also benchmark through the S3 service using CosBench. I've not put the figures up because they were wildly variable. Even on a quiet cluster, running benchmark for an hour, and then you run it again later, same length of time, exactly the same parameters, exactly the same cluster, and get wildly different outcomes, which is a bit disappointing, really. But having done all this, once we've finished with our Luminous and BlueStar upgrade, I imagine we will run these again, and maybe I'll come back to the next Ceph conference and say, look, the numbers went up. So that's benchmarking. I wouldn't get too hung up on it. Inevitably, it's going to be an artificial environment. So the migration. Migrating from Dual to Luminous, there's not much to say about it. Ceph-ansible has a rolling upgrade playbook, which does all of the things in the release notes, so you don't have to worry about, did I remember afterwards to set the right flags, because the playbook just does it for you. It was really easy. We did it on our test clusters first, obviously, but when it came to the production cluster, we updated our inventory script to know about the manager nodes, ran Ceph-ansible with the rolling upgrade playbook, went and had a cup of coffee, came back, it was all done. Brilliant. Less straightforward is the migration from file store to BlueStore, because essentially there's no two ways about it. You have to take all of the data on a given OSD, throw it away, and rewrite it. And we wrote a script to do this. It runs off a monitor node. Essentially, it logs into, it waits for the cluster to be in health OK, because you don't want to start mucking around with your OSDs when you don't have to if the cluster isn't happy. Then it logs on to a target machine, and for each OSD on that machine, it stops it, marks it out of the cluster, wipes the file system, and then remakes it using Ceph volume LVM create to make a BlueStore OSD, and it uses the same hard drive for data and NVMe partition for block.db as was used for the file store OSD. And this is a graph of the state of Ceph objects as that migration progresses. Yeah, you can see it. So this orange line is number of degraded objects. The blue line is the number of misplaced objects. You can see here time along the bottom. This is where it started on a node, so you get an enormous spike in both of these because you've just taken, essentially you've taken a machine out of the cluster and told Ceph that one's gone away, and then you make a whole new pile of OSDs and it has to backfill all of them. As I alluded to, our cluster is about 40% full, so that means you're writing 2 and a bit terabytes to every single OSD, and that just takes time. And the cluster eventually rebalances all of that, and then you can see the spike as cluster reaches health OK, and the next one starts. This process is quite I/O intensive, and if you're looking at this graph and wondering what this spike was, that was another OSD failing in an unrelated node. We found, as we've moved through this migration, that a number of disks have failed, which disk failure happens, you just swap them and carry on. To give you an idea of the timescale, this process from remaking a host worth of OSDs to the cluster being happy again takes about 30 hours. So we have 51 OSDs. This is going to be a lengthy process. When I checked before coming away, we'd done about a third of our cluster. We have about 1,100 BlueStore OSDs, and the rest are still file store. Unfortunately, this is currently stalled because our cluster has been stuck in health warn for a while with a large OMAP object. If you've run Luminous, or if you've watched the Ceph users mailing list, you'll see a lot of people talking about large OMAP objects. We've got one that appears to be associated with a bucket in S3 that no longer exists. So we're still working with Canonical to try and figure out why that happened and basically how we can get rid of it so we can get our migration going again. Which brings me on to the bit where I rant. My colleagues will tell you I could have filled this talk with rants, but I'm just a few sort of pain points we've found. Particularly, they've mostly been around the Rados Gateway service or the migration to Luminous. So when you migrate to Luminous, and suddenly you get this thing that you have to set applications on your pools. And you can do that, fine. But from administering a Luminous cluster, this application you have to set on the pool is just essentially an arbitrary string, and it's not very useful. I don't know whether that's going to become key to managing the cluster in later releases, but from our point of view, this is something you have to do in Luminous, otherwise your cluster is in health warn, and we don't seem to get any benefit from it. And I've alluded to large OMAP objects. This is a standard thing you'll get when you upgrade from Joule to Luminous, because the Rados gateway in Luminous can reshard your buckets, but if it hasn't resharded your buckets, you get these large OMAP objects which correspond to the index of large buckets. And as I say, the Rados gateway can reshard them for you, but it doesn't. You have to wait for users to put objects or remove objects from the buckets, and then the dynamic resharding will come along and say, oh yeah, it's this bucket, it needs resharding, I'll go ahead and do that. Which is all well and good, but if you've got a lot of large buckets, you've just done this migration, and you want your cluster back into health okay, you have to go and do it by hand, which means, and you can't just say to the Rados gateway, oh, that bucket, reshard it. No, you have to work out how many shards it should have, which is not hard. You find the calculation from the source code, you do it, away you go. It's just one of those things that feels like it could have been done better. And as an admin's point of view, this was a whole pile of things I had to do by hand, and I don't like doing things by hand, because if I do them by hand, I'll probably get them wrong, and it also means then that's not reproducible. If I need to do it again, I've got to go and redo the calculation. So that was a bit of a pain. Another problem we've had is that we started off everything three-way replicated because we were new to Ceph, three-way replication was easy. In Luminous, erasure coding is much better, it's much more performant. We've done some benchmarking on our test cluster, and we can get equivalent or maybe slightly better performance out of erasure coded pools than we could for replicated ones. But we now have a lot of data, several petabytes of data in replicated pools backing S3. And okay, you can say to the Rados gateway, so these users make their default pool now be this erasure coded pool, and as new things are uploaded to your cluster, great, they'll be put in the erasure coded pool, but there's no way of taking objects out of the old replicated pool and migrating them. And okay, you can do it by hand, but you have to make sure you get all the ACLs right, and you need to coordinate that with your users who might be doing other things to their buckets. And we really want a sort of administrative tool here to say both how much have we still got on our old replicated pools, and can we move some of that to our erasure coded pools automatically rather than having to either get our users to do it or find some way of automating it and be sure that we'll get it right. And that brings me on to another problem. Again, you'll have heard in the keynote, Nautilus will be able to shrink pools, but at the moment we can't. We're running Luminous, we're not going to be in Nautilus anytime soon, and we have a large replicated pool for the Rados gateway, which eventually we're going to want to shrink as we move to erasure coding. We can't do that. Similarly, we have multiple OpenStacks. We'll try a new release, we'll use it for pilot. Once we're happy, we'll start moving users onto it, and that's great. As we move users onto a new OpenStack, we can grow the pools backing that OpenStack. Great. But we're also migrating users off the old OpenStack, we're clearing hypervisors out of the old OpenStack, and we can't do anything to shrink that pool. We have to wait until everything is off, and then we can blow the entire lot away. And again, that'll be great in Nautilus, but realistically, we're not going to be running Nautilus for another couple of years, and we have to put up with these sort of things in the meantime. Our final pain point is about deployment. I said we use Ceph-ansible, which on the whole we're pretty happy with, but its weakness is provisioning OSDs. You either have to do it all by hand, so specify this drive, this NVMe partition, this drive, this NVMe partition, which, okay, you can do that. And in Joule, you specify that, and it would set them up for you and make the partitions. In Luminous, it doesn't do that anymore. It wants to use Ceph volume LVM batch, which is fine if what you want to do is to take all of your NVMe cards and turn them into one LVM volume, but we don't. We want to keep them separate, so if one of them fails, we only lose half a machine's worth of OSDs. So we're back to having to do it by hand, and this is just fiddly, and this is the sort of thing that I want my configuration management system to take care of for me, not have to do myself. So that's something I would like to be better. And also, when a disk fails, you replace it. Sometimes it will come back as a different device. You've probably seen this. You replace the disk, it was SDA. You put another drive in, it's SDCI or something. And then Cephansible will come along and say, well, I can't do this machine because we're missing SDA. And those sort of things are just, it feels like you ought to be able to automate that entirely and just say, well, there are 60 spinning disks in this box, use them. We're not there yet. Lest you think I'm going to rant for my remaining time, we're actually pretty happy with Ceph. It scales out really well. The last time we wanted to expand our Ceph cluster, as I said, we took 9 boxes, put them in a rack, and from them arriving on site, so literally coming through the door of the data center to being fully integrated in the cluster, took 4 working days. which is pretty good. If you look at if you compare that to the time to commission a new Lustre file system, last time we did that, that was several weeks. And it was several intensive weeks, whereas this, it really was plug them in, tell our phase server, which we use for the operating system install, this is what they are, they're going to be Ceph bodes, turn them on, let them install, run Ceph-ansible, go and drink coffee for several days, come back, it's all done. That's really good. It's really makes expansion so easy. Also, Ceph has been really reliable. Hardware fails all the time, and Ceph just carries on. We have now 4 failure domains, and we lost 2 racks at one point. There was an unfortunate incident in the DC. The circuit breakers, 2 of our racks were tripped, just like that. Whole thing goes dark. Ceph then obviously wouldn't write any data because it had lost 2 of its 4 failure domains. But when we got the power restored and the machines came back up and they sorted their file systems out, Ceph just sorted itself out. We had maybe, you know, a couple of dozen placement groups that needed a little bit of hand-holding, but essentially it just went back to running. And that sort of robustness has been really good for us because inevitably things go wrong from time to time. The network fails, drives fail, power fails, cooling fails, all of these things happen, sometimes quite excitingly, but Ceph just keeps going, keeps serving data, and that's something, as an admin who has a lot of things I'm responsible for, I really like about Ceph. It's pretty much bulletproof, it's really easy to expand. Yeah, it's great. And I think that's about all I was going to say. I alluded to earlier our Ceph-ansible playbooks for using Let's Encrypt with your Radis gateway. That's a GitHub URL for that. Our Ceph disk utilities, another GitHub URL there. At the moment, there still are dual and file store based scripts. We have got scripts for Luminous and BlueStore. They're not sure they're quite ready for public release. If you want an advanced copy, drop me an email and I'll let you have them on the, if it breaks, you can keep all the pieces basis. That's my email address if you want to get in touch, although I'll be here for the rest of the conference. If you want my slides, if you go to the shared app for this conference, I've uploaded them, or again, drop me an email or catch me on Twitter or something. So are there any questions? You'll have to shout. We use the... No, there's an existing... It was a question about Collectee modules. There's an existing Ceph plugin for Collectee. You have to configure it about every single daemon on the host, which we do using our Ansible playbooks. It's a template file, but it's just the straightforward. You need to get the right version. There's a different version for Luminous than for Joule. It's not compatible. They're not intercompatible. But there is now a package for Ubuntu Bionic that provides the Luminous Collectee module. So we don't have Prometheus infrastructure, so we've not tried it. The manager in Luminous exports Prometheus. I don't know how good it is because we've not tried it yet. Okay. The question over here. Sorry, I can't hear you. How do we manage the Ansible playbook? So basically they're all in Git. When we want to move our branch to a new upstream version, there's a bit of fiddly Git shenanigans, which isn't very interesting. Basically, we merge the previous branch we were working off with the new upstream as one merge, and then we merge our deployment branch on top of the result of that. And then we have a test cluster so we can test it both, does it broadly work, but the main thing you'll see change if you update Ceph-ansible is your ceph.conf will change. So when you run Ceph-ansible, you can say, don't restart any daemons, and what that lets you do is you can run it, then look at how ceph.conf has changed, and say, well, am I okay with these changes? Am I not okay with these changes? And if you're not okay with these changes, you can just back out to the previous version, and nothing has been restarted, so that's all fine. So that's what we do. We test it on our test cluster. When we're coming to do it on the production cluster, we say, don't restart anything, and just eyeball again ceph.conf to make sure we understand all the changes that are being made. And again, we have a different inventory file for each playbook, each cluster that lets us do those independently of each other. Question here.
Hi. 90% of your use is Radis. Do you use Ceph-fs or anything else like that?
It's a question about Ceph-fs. Do we use it? Short answer, no. When we started with Joule, it was still a bit sort of technology preview. I understand it's much more robust in Luminous, and I think the next OpenStack release will be looking at, can we use Manila to provision Cephafs file systems for clients sort of transparently. So that's sort of our roadmap for Cephafs. The people at CERN have been using it quite extensively and seem quite happy with it, so we'll be looking at it with probably our next OpenStack release. There's a question from the person in the blue there. There's a question about bringing a manually deployed cluster into Ceph-ansible. We've not tried it. There is a playbook, as well as the main, the thing you'll run all the time. Ceph-ansible comes with a number of infrastructure playbooks, one of which is taking over an existing cluster. People have definitely done it. I've seen threads about it. I've not tried it because we started off using Ceph-ansible, so we've not had to try that. But there is provision there in Ceph-ansible to do that if you want. Sorry, we'll come back to you, but...
Sorry, how big is your team, and how do you split your work?
There's a question about how large our team is and how we split the work. There are 8 of us in the team that manages the LSF clusters, the OpenStack installs, the Lustre file systems, the iRods file systems, Ceph, and uses sort of second or third line Unix support. What we try and do is we will have people working on particular projects and then also dealing with user tickets. So the theory is I mostly do Ceph, but when I get the ticket rotor, I then have to cover all of our systems. So I spend, I guess, about 3/4 of my time on Ceph at the moment, and that's looking after all 3 clusters. But there'll be other times when I do less Ceph and more LSF, say. And we try and mix it around a bit so that we don't just have, particularly we don't want a system that only one person knows about. So for instance, I'm here in Barcelona and I've got a colleague back home looking after the upgrade from FileStore to BlueStore, and he's been liaising with Canonical about that issue with the large OMAP object that I talked about. So it's not just me, but I primarily do Ceph. Does that sort of answer your question?
If I'm correct, you said that your pools, so your OpenStack pools and your RGW pools are on the same OSDs?
Yes, that's right.
Okay. How have you found that? How have you found sort of co-locating the latency-sensitive RDD stuff and the RGW?
Okay, so it was a question about if we have all of our pools on the same set of OSDs, how have we found that in terms of is one use causing trouble for another? So far, it's been all right. Actually, currently we have 3 Rails gateways. They're not specialist kit, they're just co-located on some of our nodes that also run OSDs. And we've generally found that you can knock the Rails gateways over, thrashing them so hard and not really impact the rest of the cluster. And OpenStack provides people with a great tool for DOSing your Rails gateway service. We're looking to, later in this year, move to having 6 dedicated Rails gateways to try and get more throughput through that S3 layer, and maybe then we'll start seeing issues with quality of service, though I think, again, in newer Ceph releases, there are more tools to manage that. Any more questions? Yes.
It's a bit of a line question. I just want to know, when you have OSDs fail on a host,
Yeah.
is there some threshold that do you replace an OSD as it fails, or do you wait for a number of OSDs to fail on a host before you replace the OSD? Because obviously you don't bring a host down all the time.
Okay, it's a question about replacing OSDs. Do we replace an OSD the minute it fails? Do we wait for a few OSDs to fail at once? The answer is, in theory, we replace an OSD as soon as it fails because we don't have to take the host down. You can pull it out the rack, open it up, pull the drive out, replace it, plug in the drive in, push it back in, and away you go. In practice, because it's another team doing it, it tends to be when they have some time, they'll go and do them. So at the moment, the person who generally does them is off sick, so we've got a backlog of 5 or 6 that need doing. But in theory, no, it's just as they fail, we'll replace them. And if you were in the previous talk, the speaker talked about you'll start to see scrub errors. So sometimes if we start to get a batch of scrub errors, we'll look for a common OSD and then go and look hard at that one, what's its smart status? Are we seeing medium errors in kernel log? And then we'll actually replace it before it's failed completely. It started to cause scrub errors, let's get rid of it now. Because replacing an OSD is very lightweight, you don't have to bring the host down, you just pull the disk out, put another one in, and away you go. Any more questions? No, I think it must be lunchtime. Thank you for your attention.